Okay, so, oh, forgot. We need this starting today because we're gonna start off, we're going to do the last leg of the semester. We've got about 6 weeks left. And we have to finish up. So everybody, triangles in your hands. I know that a lot of you are too cool to do this, but I don't care. We need to do this, so. Let's wait for everybody to be ready. So just said and said, okay, so at the count of 3, let's let all of the bad energy out and send it somewhere, wherever. So we're gonna remember Om. So 1, 2, 3. Om. Let's do one more longer this time. Om. At least I feel better. I don't know if you do. Okay, so we're talking about Ohm's law, and Ohm's law, remember, is that relationship between voltage, current, and resistance. Okay, and that's going to be the basis of everything we're going to be seeing this unit. And remember that this unit has to do with electrical circuits, and when we're talking about electrical circuits, we're talking about charges that are moving, and that movement of charges is called current. Remember, the movement of charges or the flow of electrical charge is called current. What makes charges move? Potential or voltage is what makes the charges move. And the relationship between those two in a circuit is called resistance. So another thing that's important in an electrical circuit, once we have movement of these electrical charges, we're also going to have power. And you guys probably identify the concept of power because power is this value that has to do with how much energy I can transmit in a certain amount of time. And so power is usually represented as watts. And you've heard probably the concept of watts in different settings. So if you have a sound system, the sound system is a certain amount of kilowatts. Not kilowatts, I'm sorry. It's a certain amount of watts the sound system produces. It's how loud and how strong the sound is going to come out. If you look at your energy bills, you're going to see that the energy is measured in kilowatts or megawatts. It's this amount of energy. And so it has to do with power. And power is going to be calculated very easily. Power is going to be, I'm sorry, power is going to be the relationship or the multiplication between voltage and current. The relationship or multiplication or product of voltage and current is going to give us power. And power is, let's say it's neither created nor destroyed, it's only distributed. So we're going to have certain elements in circuits that we're going to call these elements active elements. These are elements that provide power. An example of this is a battery. A battery provides power. That's active. It's providing energy. And then there are going to be other elements that are going to absorb or take that energy. The elements that absorb or take energy are called passive. And these elements are a resistance, a capacitor, etc. Remember that when we were talking about capacitance and we had these capacitor arrays and we calculated the energy, if we added up all the energy, it had to be equivalent to the energy that's provided by the power source. So energy or power is distributed. And so power is going to be voltage multiplied by current. If we have the Ohm's law relationship, which is voltage equals to current times resistance, we can substitute that in this formula and we can have variations of the same formula, depending on the parameters we have. So power is equal to voltage times current, but it can also be equal to voltage squared times resistance or resistance. Excuse me?
Which one is current?
I is gonna be current, V is gonna be voltage, and R is gonna be resistance. I just saw it a few minutes ago. I don't know what that movie is gonna be about, but I know that that is gonna be my favorite movie of the year for many, many reasons. But I love the trailer, and I think that's gonna be a very important movie.
But on May, it's Doctor Strange, and then July. I'm so excited.
I think Doctor Strange is gonna be cool because of the following, just a historical reference. The director of Doctor Strange in the Multiverse is a guy called Sam Raimi. Spider-Man. Actually, technically, Sam Raimi directed the first MCU movie because he directed the original three Spider-Man. However, I'm a fan of Sam Raimi for a whole other reason. Sam Raimi became famous when he was very young, doing these very low budget horror movies. There's these movies called Evil Dead. Google them. They are terribly low budget movies that are horror movies. It's the worst type of horror movie you can imagine. It's like Miguel is laughing. You would probably laugh watching the movie about how low budget it is, and the acting is. But they kind of set the stage for other horror movies, and he did some very creative things there. So Sam Raimi is cool, and that's why I think that the multiverse movie is going to be both weird, but it's also going to be funny. He has this sort of funny streak. But that's going to be a good movie. But the Thor: Love and Thunder, I know that that's going to be my favorite, just because of looking at the trailer. I know that that's going to be a very cool movie. Thor is one of those characters. I'm sorry about for the parentheses, but you shouldn't have asked. Thor is one of those characters. All of the characters in the MCU that have gone through the 20 movies, all of them have grown and shown certain things that have gone through them. But Thor is the only character that he was born with everything given to him, and throughout all of the movies, he lost everything. He lost absolutely everything, and he gets to a point where he's so down and depressed about that he doesn't want to do anything else. But that's not what heroes do. And so he's even fat. If you saw Endgame, so funny that seeing Chris Hemsworth's fat. But it's a kind of thing about depression and stuff like that. And his journey is curious, so I'm kind of curious as to how it ends. So I think it's gonna be a cool movie. If you haven't watched the trailer, it's out. It was out today. It looks fun. And the Guardians of the Galaxy are gonna be in it, so that's gonna be fun as well.
Also, the director is the director of Jojo Rabbit. I don't know.
Oh, it's Taika Waititi?
Yeah.
That guy did Ragnarok as well. That's one of my favorite movies. He's a very cool director. I didn't know that.
I love Ragnarok.
I didn't know if I did. Ragnarok is one of my comfort movies. I see that.
Me too. I have when
I
I'm sad,
see-
I watch it.
Yeah, I do as well.
So,
I'm gonna look for a Thor. I'm gonna look for a Thor meme for this, because the one I have. So I always put this video to remember about power. So that's just because the topic is power, and I like that video of the emperor. So remember about the relationship. Power is voltage times current, and we can do variations of this relationship with the Ohm's triangle formula. Okay. Now, the next concept that we're going to talk about is what's called an EMF. And what does EMF mean? It means electromotive force. And this can actually be very confusing, but I'm going to try to simplify the explanation as much as I can, because it's actually very simple. First off, I hope we understand up to this point the concept of voltage. Remember that voltage is the analogous to pressure. It's what makes things move. So similar to the water example, if there are 2 points that have different pressure, water is going to want to go from one point to the other because of the difference of pressure. in an electrical circuit, the concept of voltage is that energy, or that difference in energy that's created to move things. That's what voltage is. And that's what we've been talking about. So what is an electromotive force, and what's the difference between electromotive force and potential, and electrical potential? Both of them are measured in volts, and both of them are looking at the same thing, but from a different perspective. Okay, so what is an electromotive force? To simplify this, think about a battery, like your car battery. You've seen your car batteries, right? You don't know what's inside that car battery, right? But I can tell you that what's inside is some electrodes, and there's some chemical things inside the battery that are generating electrical energy, that are transforming a chemical reaction into electrical energy, right? That is an electromotive force. Anything that converts one type of energy into electrical energy is called an electromotive force, an EMF, okay? The battery example is a chemical reaction that's generating an electrical force. But we could also do that with a wind turbine, right? A wind turbine can turn around and that can generate electrical force. That's the EMF, okay? A thermal, geothermal is another example. It's thermal gas that's turned into electrical force, okay? Nuclear, that's another example. So when we talk about an EMF, we're talking about voltage, but an electromotive force is what we call what the battery is doing, okay? Is that clear? The difference of potential is what's happening. So another way of saying is that an electromotive force is what happens in the active element. That's what we call the voltage of the active element. And a difference in potential is what's happening in the passive element. Okay? And there's actually a video here that I like, the video in particular. Remember that all of this is in the PowerPoints. I particularly like this video because they use Legos, and I don't think the person really needed to use Legos, but I found it cute. And
make every exam your moment with Chegg. Keep a study partner in your pocket with.
I think it's this, yeah, it's this one.
So what I have here is something that represents a piece of wire with a charge carrier in it. And it's not going to have any kind of flow in one direction or the other because there's no difference in the electrical potential at each end. However, if I make perhaps one side positive and the other side negative, and then this figure here is going to represent the conventional current. The conventional current is a flow of these charged particles, and in this case it's going to move from positive to negative. Now,
But by the way, why from positive to negative? That's the convention that was established. Somebody said that's the way we're going to represent the movement. And that's the way we're going to understand it, because I'm sorry, if I say it's going to move from positive to negative, and then he still says, no, for my analysis, it's going to move from negative to positive. And everybody does it differently, it's going to be confusing. So somebody established as a convention, we're going to interpret the movement of current from positive to negative. Okay, that's the way we're going to. And if the current goes from positive of electrons or currents, it's going to go from positive to negative. From positive to negative. If we interpret that for everything, then we're going to be using the same baseline. So that's what you're going to be seeing a lot of that positive to negative.
inside the battery we have various chemicals here, and what they do is they cause a difference in the electrical potential between one end and the other. And if we connect this up into a complete circuit, what we tend to do then is have a different electrical potential at each end, and therefore we have the flow of charged particles, which means we have a flow of current. So here we have a very simple circuit, and what we have is the terminals, we have the positive and the negative, and by convention we have current that goes from positive to negative, so that's conventional current. Now this is our source of energy, and what I'm going to do is I'm going to represent the energy with these little yellow blocks here, and effectively inside the cell we have some chemical energy, so I'm going to leave that there. Now this is a bit of a dull circuit at the moment, so I'm also going to add some kind of component, and here we have a filament lamp. Okay, it's not quite perfect, but it's It's all I could do in Lego. So what we're going to look at is if we have this very simple circuit.
I'm just gonna, I don't know, I don't have a problem understanding British English, but I know some people do, so I'm just gonna try to, if it's going too fast. This is a power supply. And the short is positive, the long is negative. And this here is it's a lamp. It's a lamp that's being placed. Okay. Instead of filament lamp, a filament lamp is like a light bulb, okay, that's being placed here. So if I apply a voltage source or a power source to the and connect it to the lamp, there's going to be an electrical current that's being generated that's going to go through the lamp and in theory turn on the lamp.
Effectively, a cell and a light. We're going to look at this flow of energy and where it goes in that circuit. So we have this store of energy at the cell, and over time, provided there's a current flowing, this energy is going to be transferred around the circuit and it's going to be emitted at the light that we have down here at the bottom. And in order for this energy to be transferred, what we need are these charged particles. And effectively what they do is, as they leave the cell, they pick up a small amount of energy, and the charged particles move, and this is then the electric current. And as they move around, they transfer this energy from one point in the circuit to another. When they get to the cell, what they do is they release the energy and then they keep on moving. So the green man here is a bit like the electric current moving around the circuit. As it goes past the cell again, it's going to maybe pick up a bit more energy. And obviously you can see this analogy isn't perfect, but effectively what these do is this current is going to move around and it's going to transfer energy from one place to another in.
So the important thing here is that the power supply or the battery, that is an active element. That's the element that has the energy. Okay, it has the energy. The light, the light bulb here, that's a passive element. It's not distributing energy. It can absorb it. Okay, and so the current, which is represented by this soldier here, is grabbing energy from the power supply that's getting it and providing it to the light source. Okay? And that's generated by the electrical current that's flowing through the circuit.
There's a passive element and the power source is what element?
The light source is a passive element. The power supply is an active element. So active elements, again, active elements are those that are going to provide energy. A passive element receives, can only receive energy.
In that circuit. So what we have across the cell is an EMF. Now an EMF, which stands for the electromotive force, even though it's not actually a force.
That's something important as well. I don't know, usually in electrical and electronic, one thing I like about electrical, yes.
Professor, active what and passive what?
Elements, components, things, whatever you want to call them. We should call them active and element, active and passive elements or components.
Thank you.
Usually when we talk about electrical and electronic stuff, I believe it's less confusing than other areas. And I think I mentioned this when we're talking about normal physics, dynamics, statics, etc. If we talk about weight, it can be in pounds or it can be in kilograms, right? Or feet and meters, etc. When we talk about electrical things, everything is in the same unit, so we don't have to bother about that. But there are certain concepts that I don't know why they did them purposefully confusing. The reference of the energy or the voltage, it's called EMF, which means electromotive force. Or the only thing that means is that it's what's making the electrons move along the circuit. But what the gentleman here is saying is that they're calling it force, and really force is confusing because it's really energy. But it's called EMF or electromotive force. It's this energy that can move electrical charges.
This is the amount of energy transferred from chemical energy into electrical energy per unit charge. And this often has a symbol capital E, or sometimes it's also sort of like a curly E or an epsilon. And the units for this are the volt. So EMF is the energy per unit charge transferred from chemical energy into electrical energy. So as this flow of charged particles per unit time or a current flows around the circuit, what happens is they then release their energy when they get to a component. Now this charged particle is going to transfer its energy from electrical energy into other forms, and it does it across this component. And what happens is the energy is emitted, and what we have now is the potential difference. Now the potential difference is the energy transferred per unit charge from electrical energy into other forms of energy. And here we have that potential difference. Now,
So basically what's happening is that in the power source, what's called an EMF, I have some sort of energy, in this case, the battery is chemical, and it's being translated into electrical. That's the EMF, or electromotive force.
So the electrical energy starts as chemical.
It can be chemical for a battery, but it can be solar for a solar cell. It can be wind for a wind turbine. It can be whatever type of energy you're using to translate it into electrical. For these examples, they're thinking about battery. Okay, and in batteries, your car battery, the alkaline batteries, it's a chemical reaction. Okay, that's one way where we can generate energy. And then there's going to be the passive components, and the passive components are going to receive that energy, and that energy is going to cause what's called a potential difference, which is that transformation of, it's the other way around, electrical energy into some sort of other energy. In this case, the electrical energy is being translated into light. That's the difference. If instead of a light, I connected a motor here, then we're translating electrical energy into movement. Okay. But the difference is that the EMF is some sort of energy into electrical energy. The potential difference is electrical energy into some sort of other energy. It's the same thing, but the other way around. And both are measured in voltage.
Important thing to note is that this charged particle will keep moving around the circuit. And if we think about Kirchhoff's first law, we can say that the current at any point in this circuit is going to be the same because we just have this very simple basic series circuit. So this is one kind of analogy that you can use to maybe think about what's happening in the circuit. As the charged particles move from the one terminal of the cell to the other, they're moving around the circuit, and this flow of charged particles here, which is the electric current. What they're doing is they're picking up energy at the cell or the power source, and it's been converted from chemical into electrical, and therefore we have a source of EMF. As it moves around the circuit, when it gets to a component, it releases that energy and it transfers it from electrical into other forms, and therefore we have a potential difference across that component. There's going to be a difference in the electrical potential between this side and this side of, in this case, a filament lamp. Now, the current will still flow, the charges still move around the circuit, but what they're doing is they're transferring energy from one place to another. So how do we measure the potential difference? Well, what we can use is a voltmeter. Now, a voltmeter must...
I'm going to pause it here because the rest of the explanation has to do with how we measure things in a circuit. And we're going to get to that point when we do the lab exercises. There are certain ways to measure voltage and current in circuits. Okay. But we don't need to get into that right now. Okay. So just remember, the EMF or electromotive force is when we convert type of energy A into electrical. And potential difference is what we use to represent the conversion of electrical energy into some sort of other energy. I'm just mentioning this. This is actually not a thing we really need to dwell on. It's just that you might come upon a situation or an exercise where instead of saying a battery, the circuit has a battery. Remember that the capacitance exercise is that if we connect a 12-volt battery to the circuit, you might find a situation where instead of saying battery, it says you connect a 12-volt EMF. It's the same thing. So EMF, it's what's generating the electrical energy for the circuit. It's the active element. Just to mention that. Okay. Now, very important, very important. And this is just a guideline because whatever your brains do, I can't control that. What we're going to see up to this point, don't remember this for the exam on Monday. because we're gonna be talking about series and parallel resistors that behave the other way around from capacitors. Okay, so, just forget about this for next exam. Try not to get confused. I don't know what your brains are gonna do, but for some things, resistors behave the other way around from capacitors.
Hey, learn.
Why that was, I have no idea, but that's the way life and physics works.
Can we learn this?
We're actually gonna do more exercises about this after the exam, but I just want to get through this so we can advance, but just try not to get too confused. So resistors in series and in parallel. So a resistor is going to be this element that is going to oppose the flow of electrical current. And we already saw that a resistor, this is the symbol for a resistor. Oh, remember, the concept is resistance. The physical element is called a resistor. Same as there's capacitance and the physical element is called capacitance. So we're going to be talking about resistors. The units that we use for resistors are ohms, the Ohm's law. And resistors as elements can be also connected in series and in parallel. And they behave differently if you connect them in series and in parallel. We're gonna look at that. One thing that's the same, remember when we were talking about capacitance, I can have 2, 3, 4, 20 capacitors connected in an array. There are going to be series and parallel connections in those arrays. But in the end, I can have one value of capacitance that's equivalent to the whole circuit. The same concept applies here. I can have 2, 3, 4, 20 resistors connected in series and in parallel. There's a way that I can find the total resistance for the circuit. Yes, go ahead, please.
For example, when we did the capacitors, they were, for example, the ones they were like in a square. The series were like in a square.
Mhm.
And here the resistors are like in a line. They can also be in a square.
Yeah. The important thing about series is that, remember that the important thing about series is that there should be a path that is not interrupted.
Okay.
So for example, the four of you, it's like you're connected in series. There's an uninterrupted path. But I could also say that there's an uninterrupted path between you six, going from Ricardo, Lisette, Giselle, Enya, Andrea, and Vivian. So there's a square being formed, but there's an uninterrupted path. So the way I arrange them, as long as there's an uninterrupted path, they're in series.
Okay.
If there's an interrupted path that then joins again, that would basically be an example of a parallel connection. Okay, so resistors in series. This is the only thing that's the other way around. Remember that capacitors in series was the reciprocal, right? And capacitors in parallel, we added them up. That's what's the other way around. Resistors in series, we're just going to add them up. Okay, so if I have n resistors connected in series, the total resistance is going to be adding those up. Okay, going to be adding them up. Now, remember that with capacitors, when we talk about capacitors, between series and parallel, certain things remain the same and certain things change. Remember, you did that table. Same thing is going to happen here with resistors. There's three things that we are looking at: resistance, voltage, and current. Okay. So for resistors in series, the current is always going to be the same. Okay. I'm just going to write that down here. It's written there in the slide, but I'm just going to punctuate it here.
Like how the capacitors in a series.
The charge was this.
The voltage are the same. And then the charge is the same.
the resistance, the current is the same. Yeah, so the current. Oops. The current is going to be the same. And the voltage is going to be distributed. Okay. Actually, remember that this is very similar to the capacitors. In capacitors in series, the charge was the same and the voltage was distributed. Now we're just substituting charge for current because current is charge in movement. Okay. So similar to capacitors. The current is going to stay the same, the voltage is going to be distributed. And the resistors are going to be added up. Okay. Okie dokie. I'm going to give you a minute if you want to write some things down, and I'm going to jump over to the next slide. Okay. I'm going to jump over to the next slide. So let's do an example. It says a 9-volt battery is connected to a circuit with 5 resistors in series. 4 of them are 20 ohms and 1 is 10 ohms. And similar to the capacitor ones, we want to find everything in the circuit. So let's I'm gonna jump over to the whiteboard and let's draw this. Yeah, I'm gonna leave it there so you can, while I take a water break. So the first thing we need to do is to draw the circuit. So I'm going to do that. Okay, so we're going to draw the circuit. First, there's a 9-volt battery. Okay, and we're going to represent the battery like this.
The positive one is the smaller one.
The positive one is the smaller one, correct, Ricardo? So this is actually positive and negative, and this is going to be our power supply. I'm sorry. It's positive and negative. There we go. And this is the. No, give me a moment here. Give me a moment. Give me a moment. I just don't want to confuse here something. Let me check. No, actually, no, the positive is a larger one.
Then why in the Lego example was the other way around?
I'm not sure. I didn't get it that way.
Based about the Lego example.
Yeah, positive and negative, yeah. Yeah, no, it's actually the other way around. Yeah, it's a note in the Lego example. Yeah. So it's positive and negative. So this is going to be the voltage source, okay? And then it says that we have 5 resistors. Now, going back to Giselle's question about how we draw the resistors, or if they're all straight or in a square or whatever. In this case, the 5 resistors are in series, so I can literally draw them however I want, as long as there's an uninterrupted path between them. So I'm going to draw them like this. This is going to be resistor 1. Then there's going to be resistor 2. Then I'm going to put resistor 3 here. And then I'm going to put resistor 4 and 5 here on the bottom. By the way, if I wanted to, I could have just drawn the 5 resistors directly in one line and just connected it to the battery. However, as long as there is an uninterrupted path between the resistors, then it's okay. Now it says that all of the resistors are 20 ohms and one is 10 ohms. So I'm going to say that resistor 1 is 10 ohms. Resistor 2 is going to be then 20 ohms. Resistor 3 is 20 ohms. Resistor 4 is 20 ohms, and resistor 5 is 20 ohms. Now, the first thing we're going to calculate is the total resistance, okay? Now, the total resistance, because these resistors are in series, is going to be the sum from 0 to n, or from 1 to n, of all of the resistors, because they're in series. So it's going to be R1 plus R2 plus R3 plus R4 plus R5. In this case, the total resistance is going to be 10 ohms plus 20 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 ohms. The total resistance then is going to be equal to 90 ohms. What is the total voltage for this circuit? It's 9 volts, right? That's what they're telling us, that the power supply is 9 volts. So we have a power supply here that's 9 volts. That's actually going to be the total voltage. So the total voltage is going to be 9 volts. How can I calculate the total resistance that's going to be going through the circuit? The total current, I'm sorry, the total current that's going to be going through the circuit.
You can find the power first? Or it's not necessary?
We're going to do that. The power, we're going to calculate that one last. First, we're going to practice.
You use the formula current with is equal to voltage over resistance.
Correct. We're going to be using Ohm's law. So current is going to be equal to voltage divided by resistance. And so the voltage is 9 volts. The resistance is 90 ohms. That means that there's a total current of 0.1 amps. And notice that I'm drawing the current here in the circuit. It's going from positive to negative. And since they are in series, it's going to be the same current throughout the whole circuit. That means that the current for resistor 1, or the current in resistor 1, is going to be equal to the current in resistor 2. It's going to be equal to the current in resistor 3, the current in resistor 4, and the current in resistor 5 are all going to be equal to the same current, which is 0.1 amps. Yes.
voltage, right?
In the conventions that we're going to be following, yes.
Professor, and the 90 ohms would be the answer to their beat.
Yes, correct. Remember that the terms are equivalent. So we could be talking about total resistance or equivalent resistance. It's the same concept. So that would be the answer to B. Let me write those down here. This would be B. This would be the answer to B. This would be the answer to A. This would be the answer to C, which is the current in each of the resistors. And then the other thing that are asking us is, what is the voltage in each resistor? Now, because this is a series connection, the current is going to be the same, but the voltage is going to be different. So how do we calculate the voltages? We can use Ohm's law. So the voltage 1 is going to be resistor 1 times current 1, which is 10 ohms, multiplied by 0.1 amps. That's going to be 1 volt. Voltage 2 is going to be resistor 2 times current 2, which is going to be 20 ohms. My OCD. Times 0.1 amps, that's going to be 2 volts. Voltage 3 is going to be resistor 3 times I3, that's going to be 20. Actually, the rest of them are also going to be 2 volts. Because they are the same value. And notice that, and this has to do with the distribution, if we add up all of these voltages, we get the 9 volts, which is the total voltage. So again, the energy, just linking up what we talked about, this power supply is the EMF. It's what's generating the energy. And these voltages that we have here are the difference in potential how the energy is being distributed. So this would be the answer to D. And lastly, they're asking us for the power. So the power, the total power, which is the power that's being provided by the power supply, is going to be equal to the total voltage multiplied by the total current. In this case, it's going to be the 9 volts multiplied by the 0.1 amps. This is going to be 0.9 watts. That's the total power. The power that's being absorbed by each of the elements, the power of 1 is going to be voltage 1 times current 1. It's going to be 1 volt multiplied by 0.1 amps. This is going to be equal to 0.1 watts. And all the rest are going to be the same because the values are the same. Voltage 2 times current 2 is 2 volts times 0.1 amp. This is 0.2 watts. The rest are going to be exactly the same. really ugly. And we calculate the last two, voltage 4 times current 4. 2 volts, 0.1 amps. 2 watts, and power of 5 is going to be voltage 5 times current 5. 2 volts. If we add all of these up, we get the total power. Now, this is because, just to remember, the EMF, or the power supply, this is an active element. And therefore, this power is the active. It's providing power. And all of the rest of the elements are passive. All of the rest of the elements in the circuit are passive. So the active element provides the energy. The passive elements are going to absorb the energy.
Is it still 3.5?
Excuse me?
Is it still 3.5 energy in electrical power?
No, we've jumped to resistors in parallel and series. And this this would be the answer to E. Okay. Okay, questions with this one? Okay, I'm gonna save this. I'm gonna save the screenshot, but save it again. Okay.
We have two examples. Teacher, it's because in equations, I am absolutely and completely lost into everyone.
What topic are you seeing right now?
I don't know. Exactly. No, converting equations into exact ones. Teacher, it's because Mario is an excellent teacher. He does his best job. He's great at explaining.
Give me a moment, just give me a moment, give me a moment, give me a moment. Now resistors in parallel. Resistors in parallel are the way capacitors in series use the reciprocal. The same thing happens here with resistors in parallel. The total resistance is going to be the reciprocal of the sum of the reciprocals, which is what we have there. That's going to be the equivalent or total resistance. And some things are, the other things are the same as with capacitors. If I have a parallel array, yes. If I have a parallel array, now what's going to happen is that the voltage in each element is going to be the same, and the current is going to be distributed. The same thing happened in capacitors. The voltage always in parallel, either the capacitors, resistors, relays, inductors, whatever, the voltage is always going to be the same. In parallel, in series, the current is always going to be the same. That never changes, regardless of the type of component or element I'm talking about. The voltage is going to be the same, the current is going to be distributed. And the equivalent resistance is going to be the sum of the reciprocals, of the sum of the reciprocal of the sum of the reciprocals, which is what we did for capacitors in series. So this is a similar problem. We're just we're gonna read through it, and I want us to tackle this this problem. So it's very similar to the other one. We've got 3 resistors now. Those 3 values R1, R2, and R3 are 1, 2, and 3 ohms, and they're connected in parallel. And they're connected to a 3-volt battery, and we want to do exactly the same thing we did in the other one. We want to find the voltages, currents, and everything, power as well. Okay. Let me jump over. This is a shorter problem than the other one because we've got less resistors. Take a screenshot there. I'm going to jump over to the whiteboard. I'm going to clear this. Oh. This one? The solution, the complete solution is going to be on the PowerPoint. Don't worry about that. But oops, sorry, I jumped over to the one. Okay. Okay, I'm gonna jump over to the whiteboard then. So we've got, first, we've got a power supply, okay? So we've got our power supply, and I believe the power supply is 3 volts, a battery. So we've got a voltage here that's 3 volts. Then we've got 3 resistors that are connected in parallel. 1, which is called R1, and this is going to be 1 ohm. And we've got another resistor here that is R2, that is 2 ohms. Then we've got another resistor here that's R3, that's 3 ohms. First, we're going to calculate the total resistance. So the total resistance is going to be the sum of the reciprocals and the reciprocal of that, which means that it's going to be 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3, and all of this is going to be elevated to the -1. This is going to be equal to 1 divided by 1 ohm plus 1 divided by 2 ohms plus 1 divided by 3 ohms, everything elevated to the -1. Please calculate that value if you would be so kind.
I got 0.54.
0.54. Please validate.
Yes, I got this.
0.54 ohms, and this would be the answer to B. Now, similar to the other, what is the total voltage in this circuit? What is the total voltage? 3 volts. And so because they are connected in parallel, the voltage is going to be the same. So voltage 1 is going to be equal to voltage 2 is going to be equal to voltage 3, and that's going to be equal to the total voltage, which is 3 volts. And I believe that's the answer to D, actually. What's going to be different are the currents. So we're going to need to calculate current 1. Oh, we need to first calculate the total current. The total current of the circuit is going to be the total voltage divided by the total resistance, which is going to be 3 volts divided by 0.54 ohms. Can somebody give me that value, please? 5.5? 5.5? Okay, 5.5 amps. Please validate that one. And so now the currents are going to be each of the voltages divided by the resistance. It's going to be 3 volts divided by 1 ohm. This is going to be 3 amps. Current 2 is going to be voltage 2 divided by resistor 2. It's 3 volts divided by 2 ohms. This is going to be 1.5. And lastly, current 3 is going to be voltage 3 divided by resistor 3, which is 3 volts divided by 3 ohms. This is going to be 1 amp. And if we add all of these 3, it's actually going to be equal to this one here. Why? Because again, the current is distributed. And this would be the answer to C. And lastly, we want to calculate the power. The total power is going to be the total voltage times the total current, which is 3 volts multiplied by 5.5 amps. Can somebody give me that value, please? Power 1 is going to be equal to voltage 1 times current 1, which is 3 volts multiplied by 3 amps. This is easy. This is going to be 9 watts.
The first one is 16.5.
16.5 watts. Please verify. Voltage 2, current 2 is going to be 3 volts times 1.5 amps. This is going to be 4.5 watts. And lastly, power 3 is going to be equal to voltage 3 times current 3, which is 3 volts times 3 amps. I'm sorry. 1 amp.
Professor, I think that resistor 3 is 2 ohms, not 3 ohms. So
Resistor 3?
yeah, we put that as 3 ohms, and the problem is that resistor 2 and 3 have the same amount of ohms.
Oh. Okay. What's easier? Let's see. The easiest thing is to change the problem, actually, because the calculations are the same. Look for simple solutions. Yeah, it's easier to
But
change
then
it.
the total resistance will be different.
No, because we calculated everything with 3 actually.
Okay.
Yeah. Yeah, thank you for that. I'm sorry that was my mistake. This is going to be 3 watts. And so and if we add all of these up, this is going to give us the 16.5. And just to remember that the power source, this is going to be the active element, and it's basically the EMF. The power here is the active element or the power source, and these are the passive elements. And this would be the answer to E. And I'm gonna update the PowerPoint so we have that there.
Por ahí vi una foto que el sábado de la N. Ah, caray. ¿Dónde? En un sillón. Sí.